Let's talk about the third law that Newton had, Newton's third law. Okay, this is the simplest law in physics, and it's one of the most poorly understood laws in physics. It says that every action has an equal and opposite reaction, but it's a little stronger than that. It's every action force has an equal and opposite reaction force. Really, you could say every force has an equal and opposite force. Opposite meaning direction. Equal meaning magnitude. Same number of newtons. Opposite direction. And it's very misunderstood because what you have to understand is two things are really important. One, all forces come in pairs. In pairs. If you can identify any force, it has a pair, it has a partner. But the second thing is those forces are on two different objects. Sound confusing? It's really not, because here's a foot kicking a soccer ball. Well, that's a terrible foot. Here's a soccer ball. Okay. Now we're gonna if we did a free body diagram for the soccer ball, we'd have mg, we'd have the normal force, we might have friction as the ball's being kicked. But let's just look at one force, and that's going to be the applied force on the ball. That happens right there, the applied force. Okay, and let's just say you kick that ball with a force of 50 newtons. Every force has an equal and opposite force associated with it. And the force that's equal and opposite is, there's the force of your foot on the ball. Here's the force of the ball on your foot, 50 newtons. Okay, so those forces come in pairs. That should be a pairs. But the forces are on two different objects. So the free body diagram for the ball looks like this. We had normal force, we had mg, we have the applied force, maybe we have a little bit of friction, and this is, the applied force is 50 newtons. On the foot, I don't even know how to characterize all the forces that are acting on the foot. The leg is pushing the foot into the ball, so there's some big forward force. But then there's this 50 newtons back in this direction. There's some other forces, up and down forces. Okay, but these are two different free body diagrams. So you'll never see the action and reaction force on the same free body diagram. And that's a thing that confuses people. So if I said here's a block sitting on a table, right? And people go, normal force is 20 newtons. And they say, oh, that's the reaction force. It's not the reaction force. These two are equal, but they are not a Newton's third law pair. The Newton's third law pair, well, we can do it for any force. We can do it for any force. Any force, you should be able to say, what is the reaction force? Okay, and so for mg, for the block, here's the free body diagram for the block. For mg, the reaction force is the earth is pulled up with a force of 20 newtons by the block. They attract each other. Remember when we talked about weight? Weight is the planet and the object attracting each other. They both pull equally. Okay, the normal force is the force from the ground or from the surface on there. So if I drew a surface, maybe it's a table. The table is going to have a force on it of 20 newtons down from the block. It's sometimes easier to see if you label these force of something on something. So this is force of table on block. And this is the force of block on the table. Equal and opposite. This is the force of earth on block. And this is the force of the block on Earth. Okay? So there's always a pair. If we looked at the ball, again, here's mg. The Earth's free body diagram would have however much that weight is pulling up. The gravitational pull pulling up. We've done normal force. If there's friction pushing on the ball in this direction, that means the ball's friction pushes on the Earth in this direction. Okay, let's do some examples of that, because that can be a little confusing. So when you have this Newton's third law, it's the reason you would feel that ball when you kick the ball. You know you kicked the ball even if you don't see it, because the ball pushes back on your foot. You can feel that force. Okay, it's not a mysterious thing. Okay, you witness Newton's third law all the time. One of the things that's interesting about Newton's third law is it's I won't say behind every bit of transportation or motion, but locomotion, I guess I should say. The reason things move, okay? Let's look at a swimmer. A swimmer, okay? Swimming in this direction. Swimmer pushes back on the water, right? But they move in this direction. They're pushing back, but they're moving. Well, they're moving. They're accelerating because of forces on the swimmer. So here's the swimmer. And the swimmer pushes back on the water. That's the force of the swimmer on the water. Okay? So if we did a free body diagram for the water, that would be there. For the swimmer, mg, there's a thing called a buoyant force. And the force of the water on the swimmer is what pushes the swimmer forward. When you walk, okay, think of, or let's say you're running here, okay, and you're running. When you run, you push back on floor. That's friction. Okay, so the force of friction on the floor, the force of, I'll just say U on floor, the equal and opposite reaction force is the force of the floor on U. Okay, same amount of force, opposite direction. So when you push back on the floor pushes forward on you. When you jump, okay, here's bent knees. There we go, you're about to push. When you push down on the floor, right? When you push down on the floor, your free body diagram looks like this. mg, normal force. Okay, and let me write that as force of floor on you. This is force of the earth on you. That's not going to change. But when you push harder on the floor, the force of you on the floor, the amount you're pushing on the floor increases. Therefore, the force of the floor on you increases. So the normal force goes up. You accelerate upwards. So it's a lot of stuff that is kind of, we experience all the time, but we don't see it as this Newton's second law thing. Very important to understand this. Two different free body diagrams would have those force pairs. But you can always draw a force pair for any single force. You can always find an equal and opposite reaction force. The reason it's confusing is because Newton's second law comes right after Newton's third law comes right after Newton's first and second. And Newton's first and second laws deal with one free body diagram. Newton's third law helps us figure out how multiple things interrelate. So if I have a, let me see, let's do it this way. If I have a free body, if I have two blocks, block 1 and block 2, okay, and I push on block 1, why does block 2 move? Well, block 2 moves because of the forces on block 2. So let's pretend it's frictionless. Here's M1 times G. Okay, free body diagram for object 1. And here's the normal force on object 1. And we've got this applied force in that direction. Okay, now we go around. Contact, there it is. Contact, there it is. No friction. I said no friction. Hey, but there's another contact. That is a normal force. I'll just call it the force of object 2 on object 1. Let's go to object 2. Object 2 has m2g. It's going to be smaller. And then a normal force. No friction. Got the normal force. Oh, there's a normal force from object 1. And that is exactly equal to the force of object 2 on of object 1 on object 2. Sorry, force of 1 on object 2 is exactly equal to the force of object 2 on object 1. So really what happens is we can figure in intensified and regular physics, we don't have to solve this. But we could write two equations with two unknowns if we talk about acceleration, and we can figure out what the accelerations are. So for this one, and let's just talk about the horizontal, if we wanted to find the acceleration, we could say F12 in this direction. Oh, and by the way, the sizes are the same. The direction's different, but I'm drawing that with an arrow. And let's call both of them equal to F12, the same thing. So F12 equals ma. Sum of forces equals ma. So m1 is pushed by one unbalanced force. I'm sorry, I've got this exactly wrong. This is object 2, m2a. If we do the free body diagram for this one, it's F applied minus F12. Again, this is the same as this in size, but opposite direction, equals m1a. And if we know the applied force and we know the masses, we have two unknowns and two equations, so we could solve them. Okay, I'm not going to do that in here, but it ends up being solvable because of that. But I want you to be able to draw a free body diagram for those situations. Okay, last thing I'm going to talk about for Newton's third law is an example of, this really is true with a number of phenomena. It's kind of why, here we go. If we look at, well, let's just look at this. I'm going to move this like that, okay? Let me move it that way, okay? If we do a free body diagram for that object, got mg for the bottle, and I've got the normal force of my hand for the bottle, and again, here's the bottle, there's my hand. We go around, surface force, normal force, and friction. Well, if you think of it, friction was what moved it there. Friction moved it in that direction, so you can assume that the force of friction was in that direction. My hand, if I don't have a bottle there, look how easy it is for me to move my hand. If I have the bottle, it's a little harder for me to move the bottle. So for the hand, we've got all sorts of forces on the hand because it's connected to my arm. But the force of friction is opposite that direction. Okay? Think of it like this. If this was a frictionless surface, I could slide my hand like that. There'd be no push back. Okay? And there's clearly some kind of applied force from my arm here pulling on my hand. Okay? So if it was frictionless, my hand would move very quickly in this direction. Therefore, friction must be pushing back on my hand. And then similarly, if this were frictionless, there'd be no horizontal force on this object. So friction must be in this direction on that. And so you can see right there a natural Newton's third law pair of forces. So what's important? Newton's third law is easy. Every force has an equal and opposite partner force. We'll call it a reaction force. It's hard to say what's the action and what's the reaction. I don't care about that so much. But they come in pairs, but they come up on separate free body diagrams. Okay, so Newton's third law, easiest equation in the world. very difficult to conceptualize. So study these things and you'll be in good shape on it.